This lecture we will talk about the symmetry of the stress second order tensor, the stress tensor. We want to show that sigma ij is equal sigma ji. Let's pick one simple example. Here is our element. Let's draw an element here, and this is the x1 axis. Now consider this shear stress. You see, this is x3, so this will be sigma 3. Now this is the direction x2, so this is sigma 3 2. Now let's consider this shear stress. This, you see, this is perpendicular to x2, so this is sigma 2, and now the direction, the positive direction, is x3, so this sigma 2 3. Now let's this on the opposite face we have here sigma 3 2, see, and on the other side is a sigma 2 3. You see, now we want summation of moment around x1, moment of the force, okay, must be 0. You see, there is, you see, because this element is on equilibrium, so the rotation around x1 must be 0. See, there is no rotation. We're going to impose this. Here is the center of mass. Center of mass. This is called the body force. There's the body force. Now, what is the force related to this shear stress? We have to multiply by the area, because you see the stress tensor is force divided by area. So the moment of force, we want to get the force over here. You see, this is delta x1, you see, and it's delta x3. So the force is delta x1, delta x3. Here is delta x1, let's put here, sigma 2 3, delta x1, delta x3. Now, this force over here, you see the area, you see this is delta x2, you see x2 over here, so this is delta x2. And this is delta x1. You see the direction x1, this is delta x1. So the area over here, I'll raise here. The area over here is delta x1, delta x2. And here is delta x1, delta x2. Because the shear stress is projected on this area over here. And this area over here is delta x1 times delta x2. This is force. Now, let's call this Cm. Let's calculate the sum of the moment around x1. You see these four forces, you see the moment of these four forces around x1 must be 0. You see, look, suppose I have a center of mass here, and I have a bar over here. See, the same length, same length. See, if I apply a force here and a force over here, the same, but opposite direction, you see, there's a distance, let's call D, there's the same distance D. You see, the moment of these two forces here is 2 times F times D, because you see, the moment with respect to the center of mass will be Fd. You see this rotation here, you see this rotation and this rotation. So they have the same moment now times 2. The same thing can happen here. You see, sigma 32 delta x1 delta x2, sigma 32 delta x1 delta x2. This is a binary. You see, that's called binary. Now, then using the rotation around x1 will be, let's calculate the moment with respect to this point. Let's call point C, okay? That's Cm, let's call point C. Cm, okay. Now, this distance over here is, you see, delta x3 divided by 2, you see? This is delta x3. This is a half. So this distance here, you see the distance here, d is delta x divided by 2. The same distance from here, this is delta x divided by 2. Now the same distance here. Let's calculate the moment of these two forces here. So this will be, look, the rotation here, okay, is in opposite. You see, if you rotate here in the clockwise direction, so you'll be in this direction, so you'll be minus 2 sigma 32 that delta x1 delta x2 times the distance. What is the distance? Delta x3 divided by 2. You see? This is delta x3 divided by 2. That's the distance d here. You see? You see, there's the same distance over here. Now, let's calculate the sum. You see? Now, I will use sigma 23 and sigma 23 over here, this force. You see, this distance here, let's see, let's put this distance over here, you see, is delta x2 divided by 2. You see this distance over here. Likewise, this distance over here is delta x2 divided by 2. Now the area, sigma 23 times the area, the force. You see the binary force, you see here, you see the rotation. But in this case, the rotation is counterclockwise, so you'll be in the x1 direction. That's why you put plus, now 2 times sigma 23 times the area, delta x1, delta x3, times the distance d. The distance d is delta x2 divided by 2. This must be 0. You see? There is no other force acting such that the moment around x1 will be 0. You see? There is no other force. Now, the body force, the moment is 0, because the body force contains the center of mass. So the moment of all the forces that act on this element here, on the center of the element, the center of mass, around x1, it will be 0. Now, you can see clearly that this term here is exactly this term over here. You see? delta x1, delta x2, delta x3 divided by 2. Delta x1, delta x2, delta x3 divided by 2. So we can cancel this and this. And also we can cancel this 2 here. So sigma 2, 3 is equal plus sigma 3, 2. So this implies that sigma 2, 3 is equal plus sigma 3, 2. Now, to prove the other components, you just do the same. The moment you see around x2, and then the moment around x3. So we'll find out that sigma ij is equal to sigma gi. So it's proved the symmetry of the stress tensor. Direction cosines. We have done direction cosines in, I don't know the number of the video or the lecture, but I'm sure we did that. So let's see here. Suppose I have the orthonormal system. This is x1, x2, and x3. Now consider a vector, a direction I will call x1 prime, and the unit vector of x1 prime, let's call e1 prime. Let's put just, not arrow, just put like this. There's a vector. This is e1, e2, and e3. Now we can express e1 prime, the vector, the unit vector e1 prime, as a linear combination. You see, look, R3 can be spanned by the triad E1, E2, E3, by E1, E2, E3. See? So any linear combination of E1, E2, E3, you get a vector that belongs to R3. So E1, E2, E3 are linearly independent. So I can write this vector E1 prime as a linear combination. Let's put here A11 E1 plus A12 E2 plus A13 E3. So A11, A12, A13 are scalar quantities, are real numbers. Now, I will, for instance, suppose I want A11. Since E1, E2, E3 are orthonormal unit vectors, orthonormal vectors, you see, because the magnitude of each of these vector, is 1, and they are perpendicular to each other. You see, around point O, the origin. Now you see, E prime 1 dot E1 is equal. No, this will be, E prime 1 let's write down here, E prime 1. Let's E prime 1, I'll write down all this here, okay? This is E prime 1. A11 E1 plus A12 E2 plus A13 E3. See, this is, see, this over here, this is E prime 1, okay? Now, dot E1, see? This is the red one. This is E prime 1. Now, E1 dot E1 is 1 because it's orthonormal vector. Now, E2 dot E1 is 0 because they are orthogonal. The angle between them is 90 degrees. So cosine of 90 degrees is 0. Now, E1 dot E3 is 0. So from here we conclude that E1 prime E1 is equal A11. You see? Because E1 dot E1 is A11. Okay, we can repeat E prime 1 dot E2. See? Now, E prime 1 dot E2, let's write down here, dot E2. See, this is A11 E1 plus A12 E2 plus A13 E3. So this is the red one, you see? That's the E prime 1 dot E2. E1 dot E2 is 0. E2 dot E2 is 1. And E3 dot E2 is 0. So this is equal to A12. And the last one, E prime 1 dot E3. E3. This is equal, I'll repeat this, dot E3. This is A11 E1 plus A12 E2 plus A13 E3. This dot this is 0, E2 dot E3 is 0, E3 dot E3 is 1. So this is A13. Now we know that the unit vector E1 prime can be written as a linear combination of E1, E2, and E3. Now, I will draw the, instead of x1 prime, I will draw x2 prime. Let's write down here x2 prime. Let's write right here. This is x2 prime, and this is a vector E prime 2. So E prime 2. Let's put just a, we can do the same. You see, look, E2 prime is a linear combination, not the same, okay? This will be all the coefficient, see? So E2 prime is a linear combination of E1, E2, and E3, you see? The same with if I want E3 prime. Let's do this. So this x3 prime. This vector here is E prime 3. See? So we can see clearly that A11, look at that, A11 is a cosine between, you see, E1 prime and E1. This is A11. So we can write here that A11 is the cosine of the angle between E prime 1 and E1. You see? This is dimensionless. Dimensionless. You see? E1 prime dot E1 is the magnitude of E1 prime times the magnitude of E1 times the cosine between the angle between E1 prime and E1. So, you see, let's write down right here. You see, I will raise it here just to focus on x1 prime. See, what I want to show, suppose this angle here is, I call alpha 1. Suppose this angle here is alpha 1. So, cosine of alpha 1 is equal A11. You see? Cosine, you see, the angle between E prime 1 and E1, I call alpha 1. That cosine of alpha 1 is called direction cosine. So there is another angle over here, see? Let's call alpha 2. You see, look, the dot product E prime 1 dot E2, look, E prime 1 dot E2 is equal, you see, the magnitude of E prime 1 times the magnitude of E2 times cosine between E prime 1 and E2. This is A12. So cosine of alpha 2, you see, this is alpha 2. This is A12. Okay. Now, you see this angle over here, let's call alpha 3. You see, alpha 3 is the angle between E prime 1 and E3. You see, E prime 1 and E3. So, this is magnitude of prime 1 is 1, times magnitude of E3 is 1, times cosine between E prime 1 and E prime 3 is a cosine, this is cosine of alpha 3 in this figure, which is A13. You see? So we can start building or constructing a very interesting table. Look, see, look, x1 prime is equal x1 A11 plus x2 A12 plus x3 A13, or E prime 1 is equal A11 E1 plus A12 E2 plus A13 E3. Now, it's easy from now to construct this. Is this or this? You see, it's not both, you see? Or you work with x axis, x prime axis, x axis, or the unit vector. You see, I will write down here for you to figure out, this will be A21, A22, and A23. You see? Now we can prove this. Just easy. Now, x prime 3 or, you see, or E prime 3. So this will be now A31, A32, A33. You see? Now, a very important point here is this. You have x1 prime, e1 prime. We could have here x2 prime, here e2 prime. And the x3 could be like here, x3 prime, this will be e3 prime. So, again, u1 prime E2 prime, E3 prime represent a standard base also, so it's an orthonormal basis. You see, this is orthonormal basis. We could write E1 as a linear combination of E prime 1 plus E prime 2 plus E prime 3, you see? And we can see here that you just use A11, here A21, and here A31. You see? Look, you look at this table over here, you see? Now, why I can express, look at this table, you see, because this is very important. Look, E1, E2, E3, and E prime 1, E prime 2, E prime 3 are two orthonormal bases. So P is equal, P minus 1 is equal P transpose. Instead of A, you could call P, no problem, you see? So this table here is a very important. You see, we call A11, A12, A13 as P minus 1. You see, now look how I will write this. Look at here. You see, that's important because when you work with two orthonormal bases, P transpose is equal P inverse. So I can write this. This you have seen this before. You see, the transformation when we study similar matrix. This is called transition matrix. You see, I can write like this. Look, E prime 1, E prime 2, E prime 3 is equal. See, these will be E1, E2, E3. Here I write A11, A11, A12, and A13, A21, A22, A23, A31, A32, A33. This is prime, so I call this P minus 1. Or you could write, instead of A, you could write P. See, no problem. So P, 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 and P. See, P33, P32. Just call this P minus 1. Obviously, if I write E1, E2, E3, this is equal. Now I'll see the transpose. So this A11, A11, you see, A21, A21, and A31, A31. You see, the first column will be the first row. Now the second column, A12, A22, A32, 32. Now, the third column will be the third row, A13, A23, and A33. So this will be P. You see? Now, please go back and see the video about two viewpoints about similar matrix. Go there quickly and see as follows. Look, I will raise here. You see, look, it's very easy to calculate A21, A22, and A23. You see, if you want, I will do it. Okay, I will do this. Okay, I will do. Now, just for you to see how easy it is. You see, look, you just write here E prime 2 is equal. Now, A is a number, A21, E1 plus A22, E2 plus A23, E3. You see? Now, if you multiply E2 prime dot E1, you see? Now, here will be 0, you see? Look, E2 prime, you see, do you remember the red? You see, this is E2 prime, this is E2 prime. You see this E2 prime right here. E2 prime dot E1, you see, this is E1 dot E1 is 1, E1 dot E2 will be 0, E1 dot U3 will be 0. So this is equal to A to 1. You see here, A to 1. This is the angle between E2 prime and E1. Just easy. Now, E2 prime dot E2. You see, E2 prime dot E2. You see? Now, this will be, look, E2 prime dot E2. So, E1 dot E2 is 0, E2 dot E2 is 1, and E3 dot E2 is 0. So, this will be, look, E2 prime dot E2 is equal A to 2. You see, it's right here. Now, E2 prime dot E3. You see? E2 prime dot E3, E2 prime dot E3. You see, this is E2 prime dot E3. So this will be 1. This will be 0, this will be 0. So this is equal A to 3. It's very easy. It's right here. You see? You do the same. Now, instead of E2 prime, you put E3 prime. You make a linear combination of E31 plus E32, E2 plus E33, E3. You do the same. It's very, very easy. Now let's write similar matrix. This is called a transition matrix. Please go there and see the video so you can see just this. Look, I call it there as B. B is equal P minus 1 AP. You see, B here is related to prime. Let's put that's a second order tensor, okay? Be careful of this, okay? B is a second order tensor. I'll call sigma prime. This is P minus 1, you see? This is P minus 1 over here, you see? A, let's call sigma, and P is just the transpose here. You see? You go there and see how to get there. Now I presented a very important video when I introduced continuum mechanics. You see, if I use Xyz and I have the components of a stress tensor. Now, if I rotate the system to x prime, x1 prime, x2 prime, x3 prime, the components of the same tensor will change.